Let's get started with electromagnetism. Magnetic flux density and its units is the first thing we need to understand. So what is magnetic flux density? Any idea?
Sorry?
What is magnetic flux density?
Sorry, sir, I can't hear you. Can you repeat?
I said, do you know what magnetic flux density is?
Yes, a magnetic flux is basically the force being applied by the magnet around itself.
Well, basically, we don't call it just flux because flux is a different thing. Magnetic flux density represents B. It basically means the strength of the magnetic field. Okay? How strong the magnetic field is, or you can just call it magnetic field strength as well. So the stronger the magnetic flux density, that means the stronger the magnet it is. Understood? And yeah, by definition, it is the force applied by a magnet on the north pole of a magnet. Okay?
Yes, sir.
Anyways, we don't really have a very standard definition, nor it is even tested. But yeah, the units are tested and the concept is tested. B represents magnetic flux density. The unit is Tesla, okay, represented by capital T. That's magnetic flux density. Okay, apart from magnetic flux density, we also need to understand what magnetic flux is. Okay, so magnetic flux is a scalar quantity. Magnetic flux is different from magnetic flux density. Any idea what it is?
Um, uh,
We get it? What is
it is almost similar to the magnetic flux density, but at the same time, it's different, and I guess it doesn't has a unit.
Okay, so basically, magnetic flux it represents a scalar quantity. A magnetic flux density represents a vector quantity. Okay, there's a difference. Flux density is vector. Flux is scalar. Because it's a vector, it has a direction and everything. Flux doesn't. Flux doesn't have a direction. Okay, and how do you define a flux? Flux represents, the definition is simple: the scalar product of magnetic force, magnetic flux density and vector area. Scalar product of magnetic flux density and scalar vector area. So the definition is gonna look like this. Flux equals magnetic flux density dot A. Okay? It's a scalar product or the dot product, right? The dot A.
Yeah.
Dot represents the dot product or the scalar product. Now, if you were to open this up, this is going to become BA cos theta, where theta represents the angle in between the flux density and area. And now, do you know what the direction of vector area is? By the way, both of these are vectors. Okay? This is a vector, but as you do the scalar product, you get a scalar as a result. Okay? Now, do you know what the direction of area is going to be? For example, if this is a certain area, what would the direction be? Direction is always perpendicular to the area, okay? Perpendicular to the plane of the area. Does that make sense?
Yes, sir.
Okay, so if we are talking about this angle theta, we are actually talking about the angle in between this vector area and the magnetic flux density. Okay, let's see how it works. If I have a magnet right over here, this is the north pole of a magnet, this is the south pole of a magnet, and let's say I have a vector area right over here, which is standing perpendicularly. The surface is perpendicularly standing. But remember, it's a surface. So I'm not talking about the vector. The vector of the area is going to be pointing perpendicular to its surface, right? This is the vector of the area, correct? Now, the
Yes.
magnetic field lines are always directed from the north pole to the south pole, okay? From the north pole to the south pole. So from north to south. These are the magnetic field lines. Okay. Now, this is the magnetic field. Just a second, please.
Okay.
Hello? Someone, जी. हाँ, समझ लगता है कोई बात नहीं करना हाँ 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 टेबल ना हाँ 19 नंबर में पूछ अबे आसान है पीडी परीक्षा में जोड़ रखी और बतलाड़ वैसे टेस्ट सुनता है तो टेस्ट सुनने के बाद वह और यह भी अदा से कार वो पीछे ये परीक्षा में होता डायरेक्ट पे अभी मैं पारी मान करना करो वो ऐसे उम्र ना गई लगा दो पीडी दा परीक्षा वाली हाँ वो उम्र ना वाली सही हाँ ये ऐसे टेस्ट सुनना बगैर हम कारों किया नहीं तो जो लगा कर नहीं Sorry about that, Maruch. Can you hear me?
Yes, sir.
Okay. So we've got the magnetic flux density, we've got the vector area. As you can see, the angle in between them is 0, right? They're both parallel. The vector area vector and the flux density vector. Both of them are parallel, right? Theta is 0. When theta is 0, cos of 0 is 1. That means in this configuration, the flux is going to be B multiplied by A multiplied by cos of 0, which is 1. That means it's just going to be BA, which is the maximum flux, okay?
Yes, sir.
And what's minimum flux? How can you get 0 flux? You get 0 flux when the area is flat. So when it's lying down like this, so the vector is going to be perpendicular, vector of the area. And so this is the magnet, or not B, it's N. And so from here, as the field lines are generated, you can see now the angle between them is 90. When the angle between them is 90, cos of 90 is 0. And so in this situation, flux is automatically going to become VA multiplied by 0. So flux is going to be 0. So flux is 0 when the angle is 90, and flux is max when the angle is 0. Understood? Is that clear?
Yes, sir. Yeah.
Perfect. This was about magnetic flux. Okay, as a meaning to flux, what does flux mean? Flux basically means the number of field lines passing a particular area. Number of field lines passing a particular area. Okay, that's flux. And so in this situation, when the theta is 90, the field lines are not passing through this area. They are either passing above the area or below the area. That's why flux is 0. And in this case, when the theta is 0, maximum field lines are passing through the area. That's why flux is max, okay? Understood?
Yes, sir.
All right. So we just studied about magnetic flux. Let's see what's next. Flux density done. Flux. Okay, what's the unit of flux? Do you know the unit of flux? It's called Weber, okay? Represented by WB. So what was the unit of flux density? Tesla. And the unit of flux is Weber. Understood?
Yes, sir.
Okay. Now motion of a charged particle in a magnetic field. That's what we have to study. Look at it. Do you know what Fleming's left-hand rule is?
Sorry?
Do you know about Fleming's left-hand rule?
Oh, yes.
What does it say?
It's basically, it tells you the direction of the current by the help of direction of the current and the direction of the magnetic flux. You know where the force is being applied, which is by using your thumb. Though by this, I do remember a funny story our teacher
Basically,
told
yeah,
us.
you're right.
We were
We're
studying
going to use
physics.
the Fleming's left-hand rule over here to determine the direction of the force acting on a charged particle as it enters a magnetic field. Okay? Now let's assume there is a magnetic field, but this time I'm going to draw the magnetic field perpendicular to the page. Okay, I'm going to draw it like this. What does X represent in physics? A field that is going away from you towards you. X in physics means it's going away from you, okay? Understood, Maruch? Okay. Hello. Are you?
Yes, sir.
Yeah. So that means you feel lines are going into the plane. Now, this is a magnetic field going into the plane of the paper. Now, if we have a charged particle, a positively charged particle, for example, entering from the left-hand side.
Yeah.
Now, this charged particle is entering the field, okay? That's the thing. You need to understand the directions. Entering the field, okay? Now, it has a certain velocity directed towards the field. And the direction of the magnetic field lines are into the plane of the paper. Now tell me, if I use Fleming's left-hand rule, the first finger represents the direction of the field, right?
Yeah.
That's going into the plane of the paper, right? Represented by the yellow crosses, correct?
Yeah. Yeah.
Second finger represents the direction of the current, right?
Yeah. So the
current
force would be
flowing charges, right?
yeah.
So this charge is flowing to the right, isn't it?
Yeah.
So where is the thumb pointing?
Upwards.
Upwards, exactly. So that means the force that will act on this charged particle will be directed upwards. Okay? As it enters the field, the force will be directed upwards. Now, as you can see, the force is perpendicular to the velocity, right? And it will always
Yeah.
be perpendicular to the velocity inside the field, correct? Because it's following Fleming's left-hand rule, right?
Yes, sir.
Now, because it is following Fleming's left-hand rule, it will always remain perpendicular. What type of a force does this force become? A force that remains perpendicular to velocity. What is that force called? Now, I know it is magnetic force, but what is this magnetic force acting like? What is it
Induced
acting
magnetic
like?
force?
Which one?
Induced magnetic force?
No, 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 no. A force that always remains perpendicular to velocity, it's called centripetal force, FC, okay?
Oh, yes.
Centripetal force is?
Yeah, I remember when you were like
Centripetal force, the force that causes an object to move on a
motion.
circular path, exactly, or in circular motion. So as this particle enters the field, it's gonna start undergoing circular motion. Okay? The pathway that it will follow will be a circular arc. Okay? And the
Yes,
moment
sir.
it leaves the field, it's gonna again follow the straight line. Understood?
Yes, sir.
Now, because for its motion inside the circle, for its motion inside the field, it has become a circular centripetal force. All formulas of centripetal force will be applied over here. Apart from that, if you need to calculate the magnetic force, there's a formula to calculate magnetic force as well. Fm can be calculated by using the formula B multiplied by Q multiplied by V multiplied by sine of theta. So BQV sine theta is the formula for calculation of magnetic force. Okay?
Yes, sir.
Okay?
Yeah.
This is BQV sine theta, where theta is the angle between magnetic flux density and the velocity of the charged particle. And as you know, theta sine 90 is 1, right? Okay. Yeah, sorry about that. That's my son. Yeah. Okay. So BQV sine theta, theta is the angle between B and velocity, magnetic flux density and velocity, right? Theta is the angle in between these two quantities. So when theta is 90, you know sine 90 is 1, that's when the magnetic force is max. Okay?
Yes, sir.
And then because magnetic force represents the centripetal force, all the formulas of centripetal force will be applicable here as well. There are two formulas mainly. One is mv squared over r and the other one is mr omega squared. Do you know both the formulas? What does omega represent here? Angular velocity. Okay?
Yeah.
And v represents the linear velocity. So if in case this situation comes, Fm can be equated to Fc. And in that case, BQV can become equal to mv squared over r. And in that case, you can use this relationship to find the radius. Radius is mv over bq. Okay? The radius
Yes, sir.
of the path. And so with this, we finished off the centripetal force stuff as well. Let's see how much we've done. I think we've covered all of it. Yeah, we've covered electromagnetism completely. Quantitative path followed by the charged particle, that's done. It's circular path, right? We just did that. And then explain that a force may act on the charged particle in a uniform magnetic field. Yeah, that's the reason why it's undergoing circular motion, right? And this force can be calculated using the formula BQV sine theta. In most of the cases, because they are perpendicular, the charged particle enters perpendicularly to the field. That's why theta is 90 and sine of 90 is 1. So that's why in majority of the cases, the force can be calculated only by using BQV. Okay? You don't need to worry about the sine theta in majority of the cases. Understood? Okay, Maruch?
Yes, sir.
All right, perfect. So I guess, yeah, we can just stop here. If there are any questions, you may